So thank you. I think it's the time, and thank you for the video. And it's 4 already here, so I would say good morning, good afternoon for everyone, wherever you are from. So thank you for joining the webinar of the Coastal Zone Risk Mitigation and Management hosted by the AOGS. It's my honor that I serve as the host for today's seminar. My name is Xiaowen Wang. I'm from National Chien University in Taiwan, and I'm the privilege as a member in this working group, CZWG. And today, I'm so honored that we have our guest speaker, Dr. Chien from National Central University, who spent his time joining us and to share some of his experiences in remote sensing. So let me briefly introduce Professor Chien, but Professor Chien, for sure, you can introduce yourself more. I believe when you do the talk, you probably have more background experiences and insight to share with us. But I personally have known Professor Chien for many years, and he is now a distinguished professor in the Institute of Hydrological Oceanic Sciences at National Central University in Taiwan. And in the years, he has been involved in many interdisciplinary, transdisciplinary research. And one of the areas he has been actively working on include the ocean monitoring projects. And he's also part of a satellite mission. And well, in the past few years, we didn't have many opportunities to update each other, but I'm so looking forward in the next hour. He is sharing with us one of his projects that he has been recently working on. So without further ado, I would like to have you to join me to welcome Professor Chien and to start his talk. And after his talk, we can have some time to interact and with the QA. So Professor Chien, if you are ready, please.
Okay, thank you, Xiaowen. So we are all friends. We have known each other for more than 20 years or longer. Okay, so now I share my screen. And so today I would like to share a little bit about what we have been doing recently about the remote sensing technology with the target, that's the coastal ocean. So I am Chien Hua from National Central University. Okay, so we are looking at this coastal ocean. That's our target because we are talking about this coastal hazard mitigation. So the coastal ocean that play the key role in global change, both in anthropogenic and climate changes. So it is so important because more than 50% of the populations and industrial activity are within this range. But this coastal ocean is still poorly monitored by the present state of the Earth Observatory Network, both in the terms of the resolution or these processes that represent those coastal ocean systems. So in these figures, we can see the color area represent the coastal ocean, which occupies more than 10% of the global ocean area, which is significant. So in terms of the coastal ocean monitoring, the objectives can be twofold. One is to address the climate change issues. So in response to this rapid climate crisis, we have international conventions from the UN or from WNO to put more budget on this global ocean observation system. That's more a scientific aspect. The other part, that's the domestic needs. So we need to do scientific research as well as the better forecasting of weather, and also all those parameters and factors around the coastline. And also for rescues, navigation safety, engineering application such as the offshore wind farm or these oil platform, harbors, coastal protection measures, all these applications, we need the data. And also for the maritime enforcement, as you can see on the right-hand side, that represents some area that Taiwanese people or Taiwanese government need to protect or to do law enforcement around the Taiwanese water, and also some other purposes such like a military purpose. That's also some reasons. So based on those objectives, we can try to categorize all those coastal ocean monitoring network that could be in different viewpoint. First, we look at this research and operational mode. For research mode, that's the observation, the monitoring aims to resolve some scientific issues which address on the process of the coastal oceans. On the other hand, the operational mode aims to provide any data for potential users, which we don't know right now, but maybe in the future, people need such kind of data. We have to do this observation right now. So this kind of two different categories in the formal time, they are in different purpose, different way. But now in nowadays, there is a transition period. These two kinds of observation are merging to each other. So in operational mode, they are trying to obtain more observation factors so that collect more complete data set of the entire coastal oceans. That's the first type we try to categorize the monitoring. The second aspect is to consider whether the instrumentations are remote or in situ. In situ means our instrumentations can attach to the water. So in the categorized from WMO and IOC from the UN, that could be measured three different instrumentations. The first is the mooring buoy. The second is the mobile instrumentations, such as drifters or AOGS flow or sea glider, which can move or driven or brought by the ocean currents. So along this trajectory of those instrumentations, we measure the properties of the water mass of the ocean and transit back from the satellite. So compared to the mooring buoy, which is measured at a fixed point, we get this time series data. It's called Eulerian perspective. For mobile approaches, we measure the change of water mass along the trajectory we call Lagrangian perspective. And these are the two major in situ measurements nowadays. The third one is the voluntary observation ships, which provide a huge platform from commercial vessels as well as fishery vessels to install the sensors, the payload. So as we can see from the right-hand side, the dot, okay, that's a different way to project the global map. So we can see the ocean in the middle with a lot of dots of different colors. The dot, each dot indicate one measurement of the in situ buoys as well as the drifters, AOGS flow or research vessels or VOS vessels. As you can see that there is some area which is obvious, is very, the observation density is very low. This is because all those in situ measurement, they are passive, being brought by the ocean current. and due to some current characteristics, they are not be able to broad to certain area, which we mark here as the red area, for example, in South China Sea, in the Taiwan Strait, and all the way to East China Sea and Japan Sea. So that's the area, as well as here in the Arctic Ocean, where we have very few observations. So which implies that another technology is needed. So the remote sensing, especially those coastal bays, are needed to overcome this limit of data to provide more complete data over the area with low density. So this remote sensing technology can be categorized also twofold. One is the satellite borne. So we have already a lot of remote sensing satellite in orbit, providing us with SST, which is the sea surface temperature, sea surface height anomaly, the ocean color. But here I will address more on the second. That's the satellite information provide the parameters for ocean surface wave, current, and wind. So these are called scatterometer or radiometer satellite. But here I would like to share with you of some recent development. We are using the different technology, which is called GNSS-R, represent for Global Navigation Satellite System, and reflectometry. That's the recent launched Taiwanese Triton missions. So this is one of the major topic I want to share with you today. The second one is the coast-based radar. So these are the two topics I would like to share with you some recent development in Taiwan. So we start first with the coastal high-frequency radar. So look at these keywords, high frequency. High frequency represent the radio wave we are using is different from traditional microwave band. So this table on your right-hand side, you can see the designation of the radio wave or this EM wave, so ranging from megahertz to gigahertz. So usually we are using the traditional marine radar in microwave band. But here the keywords is HF radar, which working from 3 to 30 megahertz, which is much, much lower than the microwave system in terms of they have very long wavelengths of the radio wave. So this kind of radar now has rapid expand in terms of the stations. So in the year, a couple years ago, in the year 2018, in globally, we have around 400 stations worldwide. And now in the year 2023, this size has been rapidly expanded to 1,120, which is most double, nearly triple times as 5 years ago. So here, the Taiwan, we are operating 35 stations. So why this kind of HF radar is so popular or needed, so that is spending so quick? Because this kind of radar is the sole technology now that provide continuous monitoring of the coastal ocean within a large area, which can extend to the area of the EEZ, the exclusive economic zone of every country. So that makes it a unique and necessary tool to provide this ocean data, or coastal ocean data. And why this kind of radar can provide such unique area? Because they are using the HF band, which has the capability to cover the area that over the ocean, over the horizon. We call over the horizon capability, which can look beyond the horizon. Okay, so this is what I would like to show you, some capabilities of this radar and how it works. and what's the situation right now. So we go back to the traditional marine radar. That's the idea we all have. A radar transmit a signal and then receive the reflection signal from the object. The time required for the travel of the signals are used to determine the distance, and the signal, the intensity, are used to infer the size of the object. So that's a traditional marine radar, or what the idea of radar is. But these signals are propagating in a straight line. We call line of sight. So it's a line and cannot bend. So if we want to look further into longer distance, we have to mount this radar in a higher elevation. So there's a equation showing that the elevation we need is h here, and r is the Earth radius. So we can calculate the distance the signal can achieve, because it's a straight line. So if we want to look in the far distance, we have to build this radar at a higher elevated place. But you're taking the square root of this h. So when you increase a lot, you build higher tower, but you only increase a limited distance to look. So this is a limitation of the traditional marine radar or the normal radar. So how does this HF radar can do this over the horizon thing? Because the propagation of long EM wave, they have different phenomena. So they propagate in two different modes. The first one is called the sky wave mode. So for HF radar, the signal, the wavelength is over 100, even 200 meters long of the radio wave. This kind of wave, when they transmit from the transmit antenna, the TX, they can be reflected by the ionosphere, which is about 80 to 100 kilometers above this the Earth. So the reflected area can propagate long distance. So this is called the sky wave mode. Using this mode, so before the satellite era, the US or the Russia, they're using this kind of technology to detect this missile, intercontinental ballistic missile, for warning. So the range could reach more than 6,000 kilometers. So on the right-hand side, you can see that's the military sky wave mode HF radar, both in the US and in Russia. And this is called the sky wave mode. The second mode is called the ground wave mode, which means if we are transmitting long wavelength radio wave, this kind of radio wave, they can doing multiple reflections between the air and the seawater. You have salinity, so you have conductivity. So the radio wave can do multiple reflections along the Earth curvature all the way to the place that behind the horizon. So this is what is the benefit of this HF radar. So we call this HF surface wave radar, HFSWR. So here is a cartoon shows the antenna pattern can go over along the Earth's curvature to the area, reaching to several hundred kilometers, up to 300 kilometers, which is about the range of the EEZ zone of the country. So which makes this tool a particular importance for the governance to do this coastal ocean monitoring. So one note here, the range of the radar does not depend on the power it transmits. Usually people think we should get higher signal to noise ratio so we can transmit the data longer. No, it's not the case here. The range depends on the frequency you use. The lower frequency the longer wavelengths, you have more reflection effect, so can reach to far place. So we call long range distance could reach 250 kilometers to 300 kilometers if we're using less than 6 megahertz radio wave. And if you want higher resolution, then you can choose the radio wave above 13 megahertz, 20 megahertz. For example, then you can have high resolution coverage in the nearshore coastal oceans. So how many stations here? I mentioned that there are more than thousands of stations and increasing rapidly, like 100 stations per year in the recent 5 years. So this is a publication 10 years ago in the AOGS area. So you can see the dots indicated how many stations around. Now we have something very rapidly around the Taiwanese coastline, as well as the Vietnam and Indonesia coastlines. They are getting popular. So here I would like to show you what is happening in Taiwan. So the Taiwanese coastline are now entirely covered by this kind of HF radar. So this radar are supported by 3 different governmental agencies. First is called NAMR, the National Academy of Marine Research, and they operate 18 stations. And this is the second one is the Central Weather Agency. They are operating 7 stations. And the Taiwan Ocean Research Institute, which is a foundation under the National Science and Technology Council, they are also operating the stations. So here we have a coverage consisted of longer range, standard type, and high resolution nearshore to cover the entire Taiwanese coastline. And I'm honored to say that we are in the NCU, we are responsible for maintain, set up, and operate a certain percentage, like half of these take care by our team. So now this is some background of how it works. So the first or the father, the pioneer who developed this radio oceanography is Dr. Klaus Hasselmann. You might hear his name because he was one of the Nobel Prize laureate in the year 2021. So he got this Nobel Prize not because he invented this radio oceanography, that's because his contribution in climate change. But indeed, before that, he was a physical oceanographer, and he was the one who developed this technology. So here is an example. So how this radar works. So if we try to send a signal from the radar antenna to the ocean, well, there's no object, there's no vessel, no oil platform. So how can we get this signal reflected from the ocean surfaces and then sensed by our receiving antenna? So this is what I'm trying to show you how it works. So first look at this antenna. This antenna are just as simple as a stick. This is called a monopole antenna in the linear array. So all those radar, they have a linear array radar consists of 16 elements. So this radar can do multi-signal processing to identify the direction of where the signal comes from. So if we have no vessels or objective, no on the ocean surface, why we can still sense, we can still measure the reflection signal from the ocean surfaces. That's all because of the ocean waves. So the idea of ocean wave is like this picture is random, it's consisted of the superposition of many different components of the wave in different frequency, in different amplitude, as well as the direction. That's a concept of the Fourier series and also the base of the spectrum. So if we look at the ocean surface at any instantaneous of time, there must be one component coming is, for example, this one, they have their own frequency, wavelength, amplitude, and directions. The direction may coming from many different directions. So this is the idea. In the random oceans, there should be one component that satisfy a condition that cause the backscattering. This condition we call BRAC condition, Bragg scattering condition. This condition says that if the radio wave with the wavelength called lambda is equal to half, is equal to the double of the wavelength of the ocean surface, which is the component, and then we get the reflection due to the interference of construction. So this is the transmitted signal, and here is the reflected signal. If this condition is satisfied, the ocean wavelength is half of the radio wavelength when the delta is equal to 0, because that's a coastal set. So in this case, then we will have the backscattering. Then we measure something back from the ocean surface. So this is the idea why we don't need an object. We still measure the reflection from the ocean surfaces. That's the wave. And we also know the wave is moving, is propagating. So from the wave theory, if we know the wave frequency with a given wavelength, we always can calculate the wave speed or the propagation celerity using what we call dispersion relationship. So with a radio frequency, we always know what frequency of the ocean wave it interact with. And this frequency, we can calculate the speed of the wave propagation. So then we have the Doppler effect. So if the wave is stationary, like a stationary vessel, and this shows what we can measure from the reflected signal, there is an intensity of the backscattering at the 0 Doppler effect. But if the wave is moving, then we can measure the Doppler effect. And this is known by a given radio frequency. So we know that by the calculation using the wave theory, we know in what frequency we will measure the reflection. And because we all know the wave is propagating in many, many different directions, so there will be at least two. One is the receding, the other is the arrival of the wave. We will have these two signals on this Doppler spectrum. So how come if we have not only the wave and also the ocean surface current, so we can have additional shift of the Doppler shift. So this is what we are looking for, the different Doppler shift between the green and orange peak. So this is induced by the ocean surface current. So this is what we really measure to infer the surface current and also, as well as the wave. So what on your right-hand side, this panel is an example showing the product we call Doppler range spectrum, which we measure from those HF radar. And so you can see that we have two peaks, the most intensified signal. Okay, so these two peaks we call first order peak. And the deviation of this peak from the half of the radio frequency, there is a small, tiny deviation. This can be used to infer the current. Okay, so let's look at these two peaks. So this is for certain instantaneous, for 1 hour data or 30 minutes data. If we look at these two peaks along with time, then you can see this. So the horizontal axis is the time, and this signal, you can see this variation signal. They are the variation of the first order peaks from the Doppler spectrum, and they are variating, oscillating because of the tidal current. We have flood tide, ebb tide, tidal reversal, so you can always see this change of Doppler effect. So this black line is the radial frequency. So by calculating the deviation of this first peak to the black line, we can always calculate the Doppler effect. The Doppler effect is the radial velocity. So on here, you can see a radar looking different angle, and we can always estimate the radial velocity is approaching to us or receding. So the color indicate the magnitude is approaching in red, receding in blue. So if we have two stations, these two vectors can use to calculate the current for different components like north, south, east, west. Then we have the vector flow as on what you can see on your right-hand side. So we have already established that, and by using our own developed system and algorithm, so I don't have time to explain you the detail of how this can be achieved, but this is what we call Doppler spectral analysis using in the linear antenna array. Okay, so this is kind of product, and here you can see now Taiwan, we have a data that's showing the temporal variation of ocean surface current. Also, we can retrieve wave from this. And each point, we can retrieve the time series. And these physical parameters about ocean current wave, they are the basic foundation to better understand the ecosystem, like the transport of the lava or the fishery or the nutrient, other things. So this provides a foundation for the coastal data around Taiwan. So this is the first part. We have done this in recent 5 years. The second one is about the recent launched satellite, which we call Triton. Triton is a satellite aiming to measure the wind speed in the extreme conditions, such as hurricane or typhoons, when the wind is strong. So this satellite was launched last month in October the 9th. So this is some images during the launch in the South American. Okay, so you will say, we already have bunch of satellite providing us with the sea surface wind speed. Why you Taiwanese people launch another one? So this is different because this kind of technology using the GNSS reflectometry provide another opportunity for us to retrieve the high speed wind in the hurricane. Before that, we are using a scatterometer or radiometer to retrieve the wind speed. But for hurricane, this wind speed is easily over 25 meters per second, which in high wind speed. And this kind of signal is saturated using scatterometer or radiometer, which means we got high uncertainty of high wind speed data over the hurricane using current technology. And using the GNSS reflectometry, that's offer us another opportunity to get this high wind speed data by using lower frequency band and other technology. This technology we call bistatic mode. Bistatic means your transmitter of the antenna is different from your receiving antenna. So this is a bistatic mode for microwave scattering. using geometric model. So this is what the GNSS reflectometry about. So the TX is sending signal to the ocean surface, and our satellite Triton is trying to receive this signal. So what are these TX? They are not transmitted by ourselves. Actually, that's transmitted by the GPS signal or other GNSS satellite. We have now over 80 different satellites, consists of GPS from US, the GLONASS from the Russia, and Galileo system from Europe, and Beidou from China. Altogether, more than 60 GNSS satellites day and night transmit the L-band signal to the ocean surface, and we are taking the advantage to receive the reflectometry from the ocean surface. So our satellite, we don't transmit data by our own. That greatly reduces the cost, the complicated system design, and the weight of the satellite. So this is what actually the Triton satellite do. So we have GPS satellite at higher orbit around 20,000 kilometers, and we are running at 600 kilometers only. So we are receiving direct signal and also reflected signal, and we do calculate the difference between two signals to know what's happening on this specular point. So this is the idea of Triton missing. So that's make this satellite small and low cost. So what data we measure? We measure the properties of the ocean surface. So if the ocean surface is very smooth because there's no wind, it's like a mirror, we get reflected signal here. So this signal can be very strong, high intensity, but in a short time. If our sea surface become rough because of wind blowing, then we have multiple paths here in this region. This is what we call glistening zone. So data, the signal from this area can be possibly received by our satellite. So the intensity become weaker because it's average, and we have longer duration of the signal. So that's if we have even rougher seas, then the signal become more weak and prolonged signal. So that's the idea. This is what we measure. So this is very similar. If you look out the window, we are taking an airplane. So you are looking through the small round window to the ocean surfaces. You will observe such pattern like the sun glitter, the sunlight reflected by the ocean waves. And you can see this pattern like in the elliptical shape, but more round, and this is larger area. So these photos were taken 60 years ago by the Scripps scientist Carson Monk. 70 years ago. So they are using this sunlight glitter to infer the surface roughness of the sea. And this roughness is induced by wind. So the pattern and intensity of this pattern can use to infer the wind. So that's the basic idea of how we can retrieve the wind speed. But actually here in GNSS, we don't take pictures. We are measuring the reflectometry by the L-band microwave radar. So if we have a direct signal reflected at specular point, and then we receive this signal, and if the sea got rougher because of stronger wind, we have multiple paths. So this is what we try to measure, and you can think this as the pictures I show you. So if both satellites are moving in high speed, then we have also the Doppler effect. So this green line shows the iso-Doppler line. So this is what we really measure by the Triton. We don't take pictures. We measure something here. And this is in the iso delay and iso-Doppler map, we have the intensity in the delay and Doppler domain. So that's called DD map. We call DDM. So we don't take pictures. we are measuring DDM every second on satellite. So this is kind of example. Before we launch the Triton satellite, we are using the US Cyclone GNSS satellite, we call Cygnus satellite. So this is what we measure the DDM. We have also theory to transfer this roughness of the sea into the DDM. So this is what we do, trying to inverse the calculation to infer the mean square slope. Okay, so we did a lot about this normalization to get this radar cross section that is proportional to the sea surface roughness. So this is the radar cross section, which is proportional to the sea surface roughness, which is a two-dimensional distribution. And we call this mean square slope. So the mean square slope is the slope of the sea surface tilt in two dimensions and looks like elliptical shape, and the measure axis inclination indicate the wind direction. The variance indicate the wind speed. Okay, so the retrieval algorithm is first using the GNSS DDM to do calibration, normalize, to get this normalized radar cross section, and trying to use the relationship to infer the mean square slope. And the mean square slope has correlation to the wind speed. Okay, so I will show you some result. The mean square slope and the wind speed, they are not a very simple mapping, because the wave age is one factor influencing the result. So this is, we have to consider the wave characteristics. So by doing the analyze, we try to establish two-dimensional GMF. It's like this, the mean square slope inverse wave age correspond to the wind speed. By using this two-dimensional GMF, we can reconstruct the sea surface wind speed. So this is a test we compare to the ECMWF products to have this one-to-one line and do some error assessment. So this is the error assessment. This is the sample size. And in different wind speed, we can calculate the root square deviation. That's the blue circle, and also the bias. And this is a comparison. So using our current Triton algorithm compared to the existing, like the Chinese Bufong satellite or the current NASA GNSS satellite, we have the root square deviation could down to 1.1 meter per second of the wind speed. And here, before this is 1.4 meter wind speed. And in Bufong, that's more than 2 meter per second of the wind speed. Okay, so that's kind of something we would like to anticipate. When this Triton star is operation, we hope to get this high wind speed data inside the hurricane radius and provide it for better weather prediction using data simulation technology. Okay, so that's for now. So I shortly present you two topics. One is the coastal radar in high frequency, which cover the entire area of EEZ zone of the basic parameters. And this has been widely applied worldwide. In Taiwan, we are now establishing 35 stations provided in real time in the operational mode. And the second is about the Triton, the satellite. It is a satellite aiming to provide high wind speed data inside hurricane. And by using some newly developed algorithm, we hope to provide better quality wind speed data compared to the scatterometer or radiometer wind. Okay, so this is my talk. Thank you.
Thank you. Thank you, Professor Chien. Well, I personally learned a lot. And I'm just happy to see these advancements in monitoring the coastal information and ocean information. And to be honest, some of the details, I mean, I didn't understand, and this is the first time that I learned this kind of like issues and some of the details. But your presentation is very clear, so thank you so much. And I would like to check if there's any question or comments from the participants. We do have a good group of people joining. There are like 25 participants from the list. So do we have any question or comment? So Professor Chien, I do have a question. So as you mentioned, with the advancement, and if the Triton can be operated, so we will be able to have more accurate high wind speed data. And so I guess my question would be more about the application of these techniques. So what areas you think, well, the high frequency coastal radar and also the Triton can be applied, and what kind of the collaboration, if you may suggest, that you will see that working group can try to form and so on. So any application from the two techniques that you presented?
Okay, so if we think about the coastal hazard mitigation, it's always useful if we can have the alert in advance using numerical model. So like storm surge or meteor tsunami or some other huge wave impact. And for numerical forecasting, it can be greatly benefits from the real-time data. If you have the real-time data, this data can be used to adjust the model outcome, which we call this data assimilation technology. By using the data assimilation, actually the weather prediction system has improved a lot. But the one condition is you should have good quality data in the computational domain first. So if we are considering about this flooding induced by storm surge using ocean modeling system, then this coastal high frequency radar provide us the opportunity to feedback into the numerical simulation system. And this is one advantage that incorporate with numerical model. We can try to improve the quality, accuracy of the prediction products. On the hand, without the numerical model, the data itself also provide the possibility to see the moving or propagation of huge wave system. So we can monitor or we can map the wave energy over this entire area. So we can also check this high power region, that is maybe the swell or maybe some other huge wave system. And this energy is propagating not at the speed of wave celerity, but with the group wave speed. So we can also monitor that. It's very similar to the weather radar. You can see an area now is raining because you have the precipitation, the moisture coming, and you can estimate when this system will arrive in your home or when this rain will stop in a very short time. So that's a prediction of a very short time system, like in 20 minutes or in 30 minutes. And this kind of mapping over the coastal ocean also provide this possibility with the very, very short time forecasting. a few minutes or a couple 10 minutes before the event is coming. So this coastal high frequency radar could provide us these opportunities. And for the Triton, the Triton is actually a satellite that you have this orbit around the globe every 90 minutes. So it's not continuously monitored at a certain area near the vicinity of Taiwanese water. So the most advantage of this data is actually by using the data assimilation technology. So before the launch of the satellite, the Taiwanese Space Agency, TASA, has already implemented some numerical assessment on how good or if we have the Triton information, then what can benefit the prediction of the hurricane in terms of the trajectory or the intensity. So by using the satellite data, that's aiming to improve the prediction. Okay, so because this satellite provide only the data on this observation track, it's not really a map. So it has to be done incorporate with the numerical model.
Thank you so much. Thank you for your explanation and linking this data, the good quality of data, and how powerful they could be, and linking to more application. Thank you. So we have other questions or comments?
Can I have a question?
Please.
So I mean I think that we know that the climate change situation is kind of most dramatic in the polar regions. So would the Triton be getting data or receiving data or transmitting data in the North Pole or South Pole region and telemetry back to Taiwan?
The technology the Triton use not only could observe the surface wind speed on the ocean, but also be possible to get more information like the retrieve of the soil moisture over the land. That's also one important product, and also the sea ice coverage and sea ice type over the Arctic region and Antarctica area. So these are proven ability of the GNSS reflectometry can offer. And we have discussed to our international cooperator friends, especially in Japan or in Europe, they are expecting to see the data can be released because we know that the wind speed can be provided from various existing satellite systems. However, most of the satellites that are in the orbit ranging from positive and negative within 40 degrees of the latitude, they don't go to the polar region. But our satellite, the Triton, actually has the angle. So it's like a solar synchronized orbit that can visit the polar region every 90 minutes. So that's an advantage. So we are expecting to see the data, but first we should discuss or request the TASA that they should open the window for observation and the data downlink, because the satellite memory, the buffer, usually is not big enough for global coverage. They select a certain windows, like we have 3 windows now in Indian Ocean and 2 in Pacific Ocean. That's the area when they do the observation. But if we request, they will also could open the possibility to monitor the polar region. So we have really limited data from sea ice. We have more data on surface wind on the ocean surfaces, but the sea ice coverage the sea ice thickness and type is still very rare. And this Triton GNSSR actually has been proven to have this capability to do that. So it is a very promising technology in the future that Taiwanese can help the international community by providing the data like this.
So Dr. Ip, you have further comment?
Yeah, I mean, so has TASA promised to do that?
No, not yet, because their mission, the priority of their mission is to retrieve the wind speed at the very beginning. However, they also promise if there are any request from scientific community, domestic or international, they will consider to open the observation window, but that should make a formal request based on proposal. So this is we can try to organize this together with the Japanese colleague and also Norwegian colleague, because they are very anticipated to see this happen.
Okay, good luck.
Good. Okay, so we have only a few minutes left, but if there is still any question, or if you it's not kind of like you want to leave your message in the chat box, it's also welcome. Let's see if we have any. Well, yeah, the webinar, the online talk today is recorded. So later, it will be posted on our working group website. So if your colleagues are interested in the talk today, but just haven't just got an opportunity to join, so please spread the word, spread the message to those who are also interested in the coastal zone related issues. So it could be anything. So as the coastal zone are aware, we have the various and diverse uses, and sometimes a lot of times the conflicts. So how we can advance our science and technology to inform the management is always this community is trying to work. And the next step for this working group is that we are hoping to form some kind of the collaboration to encourage the interdisciplinary, transdisciplinary interaction. So if you have any thoughts, no matter it's about, well, your questions or comments to these talks, or anything that you think might be important, interesting, this working group is considering, please send us messages, email us, and hopefully that's, well, our discussions in the related issues areas can expand, and that we can together do something good for, the coastal zone. Okay, so I don't see any further questions or raising hands or messages in the chat box. So if there's no more question at this point, I guess I would just close the talk today. And I would like to thank Professor Chien again for your wonderful and interesting talk. I learned a lot and we learned a lot. And
谢谢小文。
谢谢学长. So I'll see you all guys in the next webinar. Please stay tuned. Thank you very much. Thank you.
Yeah, thank you. Bye-bye.
Bye-bye.